And here we go. For now we have 0 viewers, which is okay. Okay, I'll put this in here. Okay, well, we don't know.
Okay.
It's still at 0 viewers. This is working remarkably well.
No, I don't see a viewer. What does it say?
It says at the bottom right, 0 viewers. I don't get that.
I don't say that for me. Does everyone else see that? I don't see
No,
that.
maybe it says only for Wolfgang because
maybe,
he's the
yeah.
master.
Okay. Well, that works wonderfully. You're enjoying this way too much, Stuart.
Right. Right. You can all mark one of my assignments each. Hold on. Okay.
Okay, well, I mean, no, it's been 1 minute. I don't know what's going on. People can see me chatting in the chat room?
Yeah, I saw your last message. Okay, things should have started. Blah blah blah. Link. Yeah, can anyone join?
Okay. Maybe they're all at the other event or something.
Someone has joined. We have a visitor. Hello.
No, but it says 0 viewers.
Oh, well, in the chat it says I have joined.
Yeah.
Okay. Well.
And someone else.
Okay. Okay. Very good. Very good. Okay. Oh, we have 2 viewers now. Okay. Well, I mean, I'm Wolfgang. Hello. I guess people are slowly trickling in. We are pretty new to this technology here.
No, I can't see the comments. Does anyone know where we see comments?
Can you see the comments? Let me see. Question and answer? I guess not. Oh, yeah, okay, got it.
Oh, there we go.
So, here we go. Hello, okay. Okay, I can't connect, hello.
Oh, okay, so we have...
Oh, there's a couple of people. We have 3 viewers now. Okay, I wonder if we want to wait another 5 minutes so people can join if they want to. Now it's 2 viewers. That's right. You can hear us chatting. I mean, we cannot, unfortunately, we did not know how many participants there were, so we chose this hang air thing. So basically, the idea is that you will ask questions on the chat, and we'll answer them. I think that's the easiest thing to do. Maybe if you do this again next week, if there's something, we can see you, but can't get involved. Yes, you can. You can just write us, and we can answer the questions. Does that make sense to everyone?
So, can we actually use the chat thing here as well?
Yeah, we can use the chat thing as well. Anyways, maybe we should get started, and people hopefully will sort of slowly trickle in. Well, I'm Wolfgang. I'm one of the TARDIS Supernova mentors. And, well, I thought this might be a fun thing to do to sort of chat to the applicants and get also some questions, some interesting questions, so we can quickly answer them rather than having to type them all in. So I think I'm going to hand over to Stuart, who is at SSSim, if you want to chat to him on Gitter, and he can introduce himself, I guess.
Okay. All right. So hello. Hold on. We can see you, but can't get. Okay. So I'm trying to follow the comments here at the same time.
I think we can just mark all of these things as I don't know how we get rid of these questions. But anyways, I think the easiest thing is if you also use Gitter, because now there's quite a few things on the Q&A. So anyways, I'll let Stuart take the helm.
Okay. Okay. So I'm Stuart. Hello. I am also one of the mentors in this. I am a technophobe, so I have very little idea about all these gitters and things. So this is all kind of exciting. But I'm an astronomer working at Queen's University in Belfast, working on supernova, and so I've been working with Wolfgang on this TARDIS project for, I guess it's a couple of years now, and so it's a lot of fun to be kind of opening the doors and sharing this and trying to get more people involved. Particularly, it's already impressive to see how many of you are engaging and doing very nice sort of improvements to bits of the code. So that's great. So yeah, I mean, this is a chance to chat. I mean, I guess my as I say, I'm really on the astronomy side of things here, the astrophysics. I'm, I guess I can help, particularly if anyone's curious about why the code does what it does or how it does what it does, and so on and so forth.
Okay, well, should we move over to Marcus, maybe?
Okay. So, hello, can you hear me?
Yeah, we can.
Yes.
Okay. So I'm Marcus. I'm also an astronomer. Like Stuart, I'm more expert in the astronomy parts of the project. I don't really know about the technical details either. So if there are any questions on the atomic physics projects or what the code is doing or what you can do, well, what applications you can handle with the code, I might be one of the persons to ask. And yeah, I don't know how this all will work out, but I'm curious to know.
Good. Well, I guess we'll hand over to Vitadas.
Hello, I'm Vytautas. I'm a student. I'm a PhD, last year PhD student at Vilnius University, and I work with multi-objective optimization, and I'm mostly in charge of the fitting project. And I have been working with TARDIS for over a year. No, precisely a year now. So I have rewritten the simulation code in C as my last year's Google Summer of Code project.
Great. Well, I mean, I'm Wolfgang, as I said, and I'm an astronomer here at ESO, and I'm a technophile. So, like, I do like to try out Gitter and Google Hangouts and things like this. I'm interested to see where we can go with TARDIS this summer, and I'm gonna hand over to Michael, who's gonna unmute maybe and introduce himself.
Hello, I'm Michael. I work at MPA in Garching, and yeah, basically I work with TARDIS since now 1 year, 2 years, approximately 2 years. So basically that's
and
it.
you're also a mentor during the summer.
Yeah.
Okay. Well, I think I think now is a good time to ask questions. So let's see what questions you have, if you have any. I don't know if that all worked out. So, are there any questions? Oh, your mic is giving some noise. Well, I'll try to mute my mic. But I mean, this is a question. I agree, but the main question. I'll mute my mic. Okay. I just have to find out where. Okay, it's muted, and now just ask questions in the chat, and then we can see how things are going. Or maybe Stuart can moderate this, because as my speaker are glitching.
Okay. That's one effective way to get Wolfgang to shut up. Okay, so is anyone there? Does anyone have any questions or sort of thoughts following up some of the things you've been trying to do already, or general questions about what we're trying to do, or about either the projects or the code philosophies or the astronomy or anything of interest? What are the virtual and reabsorbed spectra in the model? Okay, that's a good question. So actually I can do some reasonable attempt at fielding that. So those are two different sort of byproducts of the calculation, and they're both important. So what we're doing in the calculation is trying to simulate light, so simulate photons propagating through the model. So what they do is you start with a spherical situation, and what happens is you get essentially two versions of the spectra. So you have an inner boundary, which is where you create your photons and they propagate outwards. And some of them get and actually escape through the top of the calculation box, and that's the normal spectrum that we're interested in. But one of the ones you asked about, the reabsorbed spectra, those are the ones that didn't get out the top, but actually got reflected back down and basically go into the inner boundary. So they're basically sort of fundamentally two classes of spectra that come out of the model: the escaping spectrum, which is what the observer sees, and the reabsorbed spectrum that goes in the bottom. So the other one you asked about there was the virtual spectrum. That is a more accurate attempt to calculate the emerging spectrum. So we do this in two ways. So if we want to actually get the emergent spectrum, you can simply do it by looking at the energy that comes out of the top of the simulation. But this virtual packet spectrum is a way of trying to get a more accurate version of that puts down the Monte Carlo noise. So it's a little bit technical how it's done, but essentially the virtual packet is an alternative way of trying to do the same thing as the real spectrum. I don't know, Wolfgang, do you want to come in and talking? The next question here is about sea-based tests.
I'll select the one on Google first, which is, hello guys, I'm working on a visualization project. I already made a PR regarding old guidelines, made my proposal according to old guidelines, but now the guidelines changed somewhat, so do I need to involve that in my application? Well, I mean, the guidelines, the only thing that changed is now that there's sort of a new way to do a PR, but if you've done a PR for the old guidelines, then this is fine. Like, just use the overview that we've given on the ideas page to do that. And there were some other questions. There is the atomic database project, and I'm getting to the C part of the code. So the atomic database project description gives that there has to be addition of metadata from other datasets to the database. What all constitutes metadata for this particular database? I think I don't know if I want to go into details right now on this. This is like, encompasses quite a few. This encompasses quite a few bits of metadata. So I think for now the main thing, or the main data we want to get from these atomic data sets is these levels, which are basically, in an atom you have sort of certain energy states and lines. And lines basically tell you what is the probability to go from one energy state to another energy state. And so basically, I think these are the main things that we do for the application. There's a big field where you sort of can go into, but I think, like, this would take too much time now. The next part was, so till now, what methods have been tried to test the C part of the code? And I guess I'll hand over to Vytautas.
Okay, so we have tried. Can everyone hear me? Oh, so okay, so we tried two approaches so far. One of them was wrapping C functions with Python wrappers and then calling those wrappers from ptest tests. The other approach that I have started doing but never finished was to just use some kind of C-based test framework. I think I used something called MuTest or MicroTest, and then the idea is to let PyTest parse the output of the C-test. So the C-test would compile into a program, and PyTest has a way of running that program, capturing its standard output or standard error output, and then parsing that and deciding based on that if the test has passed or not. Is that sufficient? I can't hear anything, Wolfgang.
Okay, I guess there's the next question. What exactly went wrong in those? So I guess I'll hand over to Vitalis.
I don't know. Nothing went wrong in those. I didn't have the time to fully implement them, and then people decided to use wrappers instead.
So if I may comment on this, like, no, I'm not as familiar as in C as I'm in Python, which is, well, that's just how it is, and I think Vitalis is our C expert, and well, Vitalis and me are our C experts. So the main thing why I thought wrappers might be an easier thing to do is because Python builds these wrappers automatically. Like when you do this, implement the C test, you somehow have to get PyTest with setup.py to build these tests. So there's a pull request already open that has exactly that issue, getting setup.py to build these. So you somehow need to have some sort of framework that makes sure that C tests are built and then run. So I thought using wrappers might be easier.
Yeah, it would be easier from the build standpoint, but I think it's also possible to make setup.py build C applications somehow.
I mean, as you see, like, either way, I think is doable. I've tried the other way, and the main problem was there to implement to hand over, like, a dictionary into a struct in C. Like, I got problems there, and it just crashed. And so this is extremely important to us that the code gets tested. We just talked about this, but it is not trivial, and so it's a hard nut to crack. Yeah.
Well, the other aspect there is that you will need to somehow know what the correct data is for the test. So if you're testing a function, it does some physics calculations, so you will need to somehow, know what the output with those parameters should be.
Okay, I think like we've dwelled quite a long time on the C stuff. So there's one question on the Google stuff, which is, hi guys, someone other than you is doing something about supernovas or similar to what you're doing. So I know I'm stickler for syntax here. It's supernova, like the plural supernova is supernova. Yes, I mean, there's many astronomers that do that. I don't know if your question was, Adrian Manjares, if your question was specific to, if your question was specifically on computing stuff, or if it's in general. Like, there's many astronomers out there that sort of watch the skies and try to understand these events. I mean, I hope that sort of answered the question a little bit. I suggest also going to Gitter, because then it's easier. We have it all in one thing. But if it doesn't like the note, just shoot us another question. And then there's the next question about the Monte Carlo simulation creates packets that are given direction with a single scalar value mu. How does mu define direction? And I don't know who wants to take that question.
Well, I can weigh in on that one. So mu is just the cosine of the angle between the radial direction and the direction the photon is going. So mu is the cosine of theta. So it's more convenient to work in terms of the cosine of the angle than the actual angle. That's all it is. So cosine theta obviously goes from -1 to 1. So +1 means it's going radially outwards. -1 is going radially inwards.
Okay. I'm wondering if there's other questions as PFRCKS. I think it's important, like, to know before one discusses these details about a project, to have basically a document, like, a draft of an application to discuss things with. So I think it's difficult to discuss something if there's no written document. So I guess, in the opinion of you guys, what do you unanimously suggest? Okay, let's do the Vibe have 4595. What do you mean? For the C tests or for what? Okay, we're gonna take the next question.
I can chip in there on. So there's no difference created by phi. That is correct. So the assumption is that the model is spherically symmetric. So the azimuthal direction, the phi direction, you assume perfect symmetry. So you only care. There's only one direction that's physically relevant, the inwards-outwards direction. So the phi direction is you don't care about it.
Okay. Well, I mean, no, I don't know what was a question with the suggest. I guess it's about the C testing. For now, like, implement it in a way that it runs with Python setup.py test. And sorry, anything else we can deal with later, I think. Yeah. So I think anything else we can just deal with later. If you can get Python setup.py test running and test part of the C code, I think that's great. Either way is fine, and I think like if you can crack it one way, you can crack it the other way. It's not easy, and so I think like I think this PR specifically will teach you a lot about Python, C, and interactions with Python. Good. Okay. Are there? So we'll see. I mean, no. You can see, but can't get involved. So I don't know if there's any other questions for now. Okay. Well, if I don't know if this was useful for you, but yeah, we might attempt this again, maybe in a week's time. But we'll see about this. We'll see how the mentors have time or don't have time. I don't know. What do you guys think? The people in Hangout, is there something else we want to add to what we do with TARDIS? Maybe should we do a quick overview? What do people think?
Right, so there's another question just come up now.
Okay. Well, I'll let I don't know. I guess Marcus would be. Marcus might have some idea about this, or Michi. I don't know. Who wants to take that question? Okay, Marcus.
Well, I think you or Stuart should comment on this because it's you're setting the strategy. That's not me or Michi. I could comment on this for the physics, but
so.
Yeah.
I mean, no. Well, then we'll comment on this. So TARDIS is specifically designed to run fast. I mean, all the projects that we've put up sort of are stuck together. I mean, one of the main applications of why TARDIS was written was to be able to fit stuff. So this fitting project is specifically is like one of the first sort of more scientific attempts of TARDIS. And if you would make this 2D or 3D, then it would not be as fast anymore. So for now, we're going to concentrate on 1D, and why Stuart and Marcus have a code that is much more physically, that has much more microphysics built in, and is 3D as well. And it takes longer. It takes longer to run. But I mean, so we sort of have different approaches to this. So we will try to fit things while they will have a model and model this, and so we can compare what makes more sense. I don't know if that's a fair answer to what we're doing. For now, it will be 1D. I think that's the main answer. And then the next question is, and also could you suggest some reading to understand basics of the physics involved? I don't know. I think maybe someone who's teaching, which is Stuart, might be able to comment on that. Stuart? We can't.
Right. Okay. Sure. Yes. So someone else has already helpfully posted a link there. So there is a so V Pruzo has just posted a link to the sort of ideas page here.
That's only astronomy knowledge needed, and it says an astronomy knowledge needed, yes or no. I think the question was more like to know where can they go. So
Yeah, but what I'm saying is that there is on that page, there's quite a lot of background information about
I see.
what the supernova is, what a supernova spectrum is. So there are figures there that you can read about, sort of principles of what it is, the objects that we're trying to understand. So if you're looking for astronomy background, that is a sort of sensible place to start. If you actually want to get into the rather than the the physics of the supernova, or rather the question of what is it about the supernova. If you want to get into the background of what the code is actually doing, this is the theory of rate of transfer, basically in spectra in supernovae. There are a couple of good undergraduate, graduate level textbooks that I would kind of recommend. So on radiation processes, see if I can find a copy of it.
But I wonder if that will be available to. Well, I guess you guys are all at a university, so you can just check it out. So all of the I should mention that I think we always
These are both
appreciate
good books.
we always appreciate if people are interested in the physics, and it's great. It helps you fulfill the project much better. But I think it's not super necessary, but it's great if you're interested. So if you can show the books again, sorry, Stuart.
Yeah, so this is a very good one on sort of basic principles of astrophysics or radiation processes in astrophysics. If you read about that, it will tell you about a lot of the basic mechanisms that actually cause. So if you look at that web page that was linked, you'll see about the sort of spectra we're trying to simulate, and this tells you a bit about it. And this is also a standard textbook in the field, the theory of stellar atmospheres, which is talking about how, again, the various fundamental processes of how atoms are excited, how they imprint spectral lines, and so forth. Those sort of texts are good starting points. There are much more advanced texts. I mean, if you look if you look in a library for books, basically it's the theory of radiation transport. You can get a lot of the basics from that. Yeah, so that would be sensible places to start off.
And I guess the next question I'm also going to field to Stuart, because he's been using the GUI quite a lot as a teaching tool. What functions do you expect the GUI to perform?
So the GUI, there are a lot of things that would be nice for the GUI to do. I don't know how much this has been discussed already, but I think the ability to visualize the model fundamentally, I think, is really useful. So at the moment, the GUI that we sort of are working with. So one thing that's lacking is any kind of clear documentation. That's something we definitely need. But at the moment, what it basically does is it visualizes things like the temperature and this dilution factor, this TR and W variables that are around the code. But it would be nice to have more information actually visualized. Actually, also, at the moment, it has functionality where you can sort of click and select your way through a hierarchy of menus and find out information about the structures of zones. It would be nice to be able to get more visual information from that, so rather than just tables of numbers, for example, to be able to make a plot of things, at the moment you can click through and get tables of ionization fractions and so on, it would be useful to get more sort of visual aids for that. A functionality I think would be really useful for the GUI, which I don't know if someone has already been looking at, but at the moment, when the code is running, the GUI is basically not active. So the code runs as a sequence of iterations, and I think it would actually be useful as a user if the GUI was continuously updating the various images it has, so that you can actually watch and try and understand, for example, how a model is heading towards convergence and so on and so forth. That's actually one of the main things that would be appreciable right now.
Okay, I think adding to this, one of the ideas with the GUI is sort of to have it stand alone, so you download it on, like, a couple of us has Macs, and there's also people that with Linux that you can just, for Mac, download a DMG, or for Linux there's like a DEB package, and you have like you double click on the desktop and it opens up and you basically see a nice little thing, and you not only visualize the model, but you can already also specify what's going on. So you can change the different parameters and then click go, and it basically runs the code itself. So sort of a standalone application that would help a lot. Like, while we have, for us it's easy to do these YAML files. For many astronomers that would like to use this tool, like, this is specifically aimed at, like, astronomers that don't do a lot of theory. It would be nice for these people to have sort of drop-down menus where they can see what options are actually available. And so I think that's one way we want to go down the line. So Kaushik asked a difficult question: where does TARDIS see itself 3 to 4 years down the line? I don't know. I think for now, well, I mean, no. I think it's easier to, it's always easier to think about 1 to 2 year scales. In 1 to 2 year scales, what we want to do, there's a couple of things. The fitting part will be a big part of TARDIS. That's one of the main reasons why TARDIS was made, to be able to fit a lot of spectra. There's no open code out there that can do this, and there's no fitter out there that automatically fits the spectra. That's a difficult thing. So the main thing that people have done so far is manually fit spectra and then get the parameters out. And so you can do this, but it takes you a long time, and it is very difficult to actually formalize what exactly are your criteria for a good fit. And so we want to automate this, and one of the ideas is to sort of like run 100 or 1,000 supernovae and then fit them with TARDIS. The other part where we're heading is what Michi is mainly implementing. Is we're implementing new microphysics. So for now we do type 1a supernovae, which are the explosions of a sort of a dead star like a white dwarf. But we also want to do the type 2 explosions, which is sort of the collapse of a massive star greater than 8 times the mass of the sun. And TARDIS also makes quite a few assumptions about several microphysics parts, and we want to test if these assumptions are good or not. So it's built in a modular fashion. That means it's built in a way that we can just implement new physics, switch that on, see if it makes a difference, and if it doesn't make a difference, use our assumption that might be faster. Okay, there's a new question. I hope that answers your question, Kaushik94, for now. The next one was, for the proposals, is there a particular template that needs to be followed? And I'll let Vitatus field that question. You need you to unmute.
I personally recommend using the GNU template because it sort of provides a good structure. I can paste that into Gitter maybe. I think it makes a lot of sense this way. But to answer, no, I don't think we require you to use any kind of template.
Yeah, I think the main thing is, we want to see what you want to do over the summer, and like to know, we're here to guide. Google specifically says we're mentors. We're not supervisors, and so like to know, we give sort of projects, but we also want you to think about how you would approach that project, rather than us giving you a step-by-step instruction.
Yeah, at least try to include all the sections from the GNU template, I think.
Okay. So the next question was, how much has TARDIS succeeded in achieving its goal? The aim was to provide a time and computation efficient solution. I think, it has. It runs, it takes, I don't know, a couple of minutes. The example file is much faster than the calculations that are more realistic. It takes roughly 5 minutes. And I think, it's been now 1 year since the release, and I think we've made great strides. Vitatus specifically has been able to actually attempt to fit something. But for now, this is all wrapped in the Dalek part of the code, which is not very well documented and has many things hard coded. So it has been very difficult for us to try things out. And all of us also have. This is an important project for us, but all of us also have other we all astronomers with other supernova related projects, and so Google Summer of Code gives us the opportunity to actually work with someone and try to get this further. I hope that answers your question, PFRCKS. The next question, how do you go about fitting the spectra? Do you have an experimental graph and you start changing parameters to try to reproduce it? Yes, we do. We don't call it experimental graph, but we'll call it observed spectrum. And so we'll try to fit the observed spectrum, but as TARDIS runs, as TARDIS does not include all the physics, all the realistic physics, which none of the codes does. All simulations do make assumptions to make it feasible to calculate this. It doesn't reproduce it perfectly, and that's, I think, one of the challenges that will come. But I think the fitting part, maybe Vitautas and/or Stuart can comment on that, how far we've come and what we've done.
Well, we managed to we right now we use a simple RMS for comparing the spectra, and so we used, for example, differential evolution, and it basically succeeds. It finds it reduces the error to a very low value, more or less to the point where it's more or less to an optimal point. However, I think that the parameters it finds are not perfect.
It's not perfect, so we've discovered degeneracy. I don't know if that means to something like parameters that fit equally well. This makes it more difficult, and that's something we want to work on. And the main thing that we want to work on for the fitting project is that we want to have this modular, so we can easily plug in different sort of fitting functions and have it better documented than it is currently documented. Some of you have dug into Dalek, and I've appreciated, with very little documentation, you've figured out sort of how to run it. But we don't want to go down that path, so we would like to have it better documented and have an actual API that we would like to I think we would like to do over at GSOC. So Aditya says, is there room for significant optimization in the time it takes to simulate and synthesize a spectrum or spectra? A spectrum, so spectra is plural. I understand that the speed of the fitting process is constrained by the simulation speed of TARDIS for a generated config file. So I don't know if Stuart or Marcus want to comment on this.
I think what they mean is that can we improve the actual simulation to run faster?
Yeah,
So I think this is a very good question, and I think I think actually having a good answer to that question is something that it would be good for us all. So my impression, but it's an impression right now, is that it is unlikely that we can speed things up hugely more, because we have spent a fair amount of time trying to do that. But it's important to be aware that at least me, Marcus, and this is true of Wolfgang, I think, as well, none of us are really wizards when it comes to writing computer algorithms. And so our implementation is based on a logical, or what we believe is a logical way to try and describe physics. But it may be that there are bottlenecks that come from profile. Now, we've spent quite a bit of time has been invested in trying to profile and figure out what the code is doing, and we believe it is pretty efficient. But the point that's being made here is very correct, that the optimization, a key ingredient is how quickly you can synthesize a particular spectrum. And so it is definitely something that's worth looking into. As I said, we've looked into it a bit, but I don't think we have a definitive answer.
Well, I think I should jump in here. Well, we didn't we looked into this over a 3 months GSOC project last year. Well, we TARDIS looked into this, and I think as far as we can tell, like, you know, given, like, you know, if you don't change the algorithm, like, you know, making sure that we just try to multiply where we multiply instead of dividing and things like this, given the algorithm that we want, I think we're as fast as we can go. The question is, one can change the algorithm. So this is one of the things that we were sort of talking about before. We want to make this modular in the sense that we can see if we can make faster approximations to the physics that are minutely wrong, but solve the question much faster than the current implementation. So this is what we want to do. See, like, to know what is really necessary to produce an actual spectra, and then see if there's ways where we can sort of cut corners, but that don't necessarily hurt us in the physics. I think speed is important, and that's why Vitalis did this last year. I mean, you know, he rewrote a lot of the stuff into C, and it's very good. I'm wondering if this is something, if this is the direction we now want to go into. I think, like, you know, there's many other questions about the fitting. So a good friend of mine always told me, like, you know, beware of premature optimization. Like, you know, it's great that, like, you know, we can make it faster, but I think first of all we should figure out how to actually do the fitting and get the fitting right, and then, like, you know, we can think about how to make it faster, and then we will also realize what are the bottlenecks, or maybe we can figure out some clever way of recreating spectra without actually running TARDIS all the time with something interpolation. I hope that answers your question, Baditya 04. The next question that I sort of see is the Kaushik question, and I'm going to answer it from the back, which is there really a scope for projects like testing? Oh, there is really a scope. So we discussed this just now, and we have a huge problem. So one of the goals, for me at least, for TARDIS was to have an actual continuous integration. That means we run tests every time we commit, and we have some of this, but we don't have all of this. Like, for me, this is extremely important to see, like, you know, when we introduce new features, that they're properly tested. We just discussed this now with, like, you know, an unusual result that someone performed with our code, and we were wondering, like, you know, is this real, or was there some bug introduced over the last year? So I think, like, you know, testing is very important, and, like, you know, someone can go through and make sure that we follow proper code standards and can make sure that things work well. I think it will make it much more maintainable and much easier for the project in the future. The other things, how about breaking down project to 2 to 3? I don't quite know what you mean. The fitting algorithms by scikit-learn. So as TARDIS takes 5 minutes to run, we can't, like, you know, I don't know what scikit-learn. I mean, a lot of these algorithms take like 20,000 function evaluations, and 20,000 times 5 minutes is a little bit difficult. Well, I mean, you know, I'm an impatient person, but I think even for the most patient persons, that's a long time. So what we do is we use IPython parallel to just distribute this on, like, you know, many cores. Like, you know, we currently use 40, but we want to go up a little bit more, and there's another question about this. And so we can't easily use this scikit-learn because it sort of needs to push the questions to IPython parallel, and needs to push multiple evaluations. So I think it's much easier to implement some of these algorithms. That's why we have Vitalis on staff, who's, like, you know, someone who knows a lot about how to quickly implement these algorithms, because most of them are not designed to be run the way we need them to. The next question is, are there any plans to make use of GPUs on either the Python or the C side of things? I don't know if anyone wants to answer that question. So I can take this. Well, I mean, GPU rate of transfer is a little bit difficult. So I looked into this very briefly. I'm not an expert on this, but I looked into this, and one of the things that I realized is that GPUs sort of need to have a stream of data and then execute the same thing at the same time. And this is difficult to do with Monte Carlo. So what our Monte Carlo little packet does, like we sent 40,000 packets through the simulation, it goes and then it finds a point where an interaction happens, and then it basically sees if it interacts. If it doesn't interact, it sort of goes up. If it interacts, it chooses a new direction, and it's sort of like a random walk and goes out. And it's difficult to do this on a GPU in parallel with many packets, because maybe some packets interact and others don't. So I have the feeling that yes, you could do it in GPU if you had infinite amount of time, but our main goal is to get interesting signs out there, and I think we have it fast enough, and that sort of answers the other question as well. Michi has implemented some OpenMP stuff, so TARDIS can run in parallel, which I guess is sort of Gautam's next question. It can run in parallel, but it's very difficult to run this on the GPUs. I don't know if that answers. I mean, that answers quite a few of the questions now. I think that's for now the questions. The principal. Okay. Good. I don't know. Does it? That's great. I didn't use multiple cores. Well, it doesn't. Well, so each TARDIS run for now is single processor. But if you wanna evaluate 200,000, if you wanna have 200,000 function evaluations, we will run multiple TARDISes independently with multiple different parameters in parallel. The thing that Michi has done is also make the TARDIS itself parallel. So when we send all these little Monte Carlo packets through the envelope of the supernova, it basically you can split this up onto multiple cores, and that's what Michi has implemented. And there's a pull request in this, and hopefully soon we will have this tested. Another thing that needs testing and implemented. So for now, TARDIS is single core, but if you run TARDIS through Dalek, it's multi-core. So in the end, we've applied for time, and we have 200,000 CPU hours, and we sort of think about 500 cores per fitting run, and that hopefully should speed it up to, I don't know, each fit taking a few hours. How about merging testing project with the Plasma project? I mean, in the end, it's whatever. I mean, that's right. I mean, Plasma project was started because we also felt it's not very modular and it's very difficult to test. And I mean, in the end, it's not these are the projects that we say these are the only projects. I mean, talk to us. If you say I think this goes together very well, then write down an application for this. I don't think I think that might be a good idea. I agree with that. Yeah, I mean, make an application that includes that. I think that's very sensible. I think both of these. I think there will be a lot of testing for the Plasma project, and there will also be quite a bit of new modules for the Plasma project. So we're Stuart and I are thinking of some microphysics stuff that we actually want to implement. Good. Does that answer people's questions? Are there more questions? I guess, should we give this another 2 minutes? And if there's no more questions, we'll sort of stop. We'll still have 10 minutes left. Does that make sense to everyone? Yes? No? Yes. Yeah? No? Okay. Okay. Well, does this answer your question, Kaushik? 94. Maybe it does, maybe it doesn't. Good. Okay. Well, it's still. Now's the time, people. Yeah, I mean, no. In general, maybe I should add this. I think there's questions. No, there's no questions here. I think in general.
Who named the project?
That's very good. Well, do you want to take the? Okay, well, I mean, I'll take this question. So very originally, we had this fitting project. I did this fitting project for my PhD thesis way back when, and I like Doctor Who. And I had an autofitter that drove a code which did the same thing as TARDIS but was not open. I think most of us are, to Gautam's questions. And we wanted to, well, I mean, no, I wanted to have an open code that does the thing that TARDIS does now. And so in the end, we said, well, I mean, no, if if the fitting code is called Dalek, well, what do we name the big code? And so Stuart was a physics driver behind it. I didn't know much about wave transfer, and like he basically taught me most of it. And we both like Doctor Who, and so we said, well, I mean, if one of them is called Dalek, why not call the other one TARDIS? And so that's how it is for now, until we get sued for copyright infringement. But for now, that stands. About the web-based interface project, what exactly do you want it to do? I mean, why is it needed? I already read issue 241. I don't know. Michi had some comments about this before. Do you want to field that question, Michi? You need to unmute your microphone. Yeah. No. Well, once you unmute it and then it mutes again. Okay, well, I can start. Well, the main thing is, like, I don't know, we want people to be easily run this code. For now, I mean, all of you could relatively easily. Oh, Michi's there. Go ahead, Michi.
So where we were. So sorry. Hello?
Yeah. So about the web-based interface, what exactly do you want it to do? I mean, why is it needed? I already read issue 241, and I think like you had some good pointers about this stuff before, about why we think we need a web interface.
Maybe we don't need a web interface. It was only maybe an idea to bring TARDIS to people, that they can use it easily. So you don't have to install the whole code in your computer. You simply go to some web interface and then run your model. And the only restriction is that the model should be free.
Yeah, I mean, maybe to elaborate on this. So, I mean, you all are you're quite experienced using computers, so you know. Well, I mean, astronomers do as well, but I think it's easier. It's difficult to install. Like, if you don't have a lot of time, many astronomers, they have a spectrum, they observe the spectrum, they quickly want to find out how can we match this to something. And so for many years it was that people had proprietary codes. They sent their spectrum to a person with a proprietary code. This person would like make the analysis and send the analysis back many months later. And now, like, we have TARDIS, but I mean, TARDIS is not super simple to use. I mean, it took you all some time to sort of get it installed. So we would like to have something that people can easily, like, interface with, and basically go there and put their spectrum in and then see what fits. I mean, in the end, the web interface is designed. So Roland, who's another mentor who unfortunately couldn't make it, suggested that in the end, you upload a spectrum and TARDIS will run with a fitter in the background. I mean, as I said before, it all sort of ties together. We'll run with a fitter in the background and we'll provide you a fit. And with the web interface, you can sort of adjust this fit and see how things change. But in the end, the web interface is mostly there to make it easy for other people to use this code. And not only just general research astronomers that want to fit their spectrum, but we also want to bring this into classroom. Like, when Stuart teaches about wave transfer, it would be sort of nice to say, well, I mean, play with this, and they don't need to install it. I mean, some people have Windows computers, and so for them it's difficult to install it. I mean, we don't support TARDIS on Windows, and they can just go to a web page, run the thing, play around with the parameters, and see what goes. And as Michi mentioned before, we also want to make sure that, if you run the models, they're shared with the community. So any model that is run, is there for other people to use. And yeah, I mean, that is the main reason why we think a web interface would be very, very useful. We'll be the mentor for the GUI project. I think the mentor for the GUI project will probably be Stuart. And myself as a backup mentor. So we sort of both had requirements for the the GUI, and sort of we both programmed together. But I think it's maybe a little bit too. I mean, no, we will all sit down together and see what, as you write the as you write your application, and sort of your application might not necessarily be exactly the thing that we wrote down on the ideas page. We might try to align, like, what you write in your application with someone who's experienced in this. The documentation for TARDIS is sparse of now. Can something be done in that direction? Oh, it definitely can if someone does. It will make things a little bit easier. I mean, yeah, I mean, we didn't put up a documentation project because apparently Google Summer of Code doesn't allow this, but we need people to write documentation. Unfortunately, it's very difficult for us personally, as we are pretty much very much time limited to do that. So if you want to do something about this, then this is a sensible. This is like definitely something that we're interested in. Okay. Good. Okay. Yep. Good. I don't know if there's any other question, but I think now, I don't know if there's no more questions within the next minute. I think we'll stop here, and we'll see if we'll have time next week. But I don't know, we'll need to discuss, because we all have schedules and travel schedules and things like this, so it's not always easy to make sure that everyone has time at the same time. Good. Well, I mean, I don't know. Other than that, thank you very much for your participation. I'd like to know, it's great to see so many people interested. Do ask questions. Do ask. Do like to know if you have something. If you're not quite sure, put the PR up there. We don't mind if the PR doesn't work, but it's just so much easier to discuss on an actual pull request rather than discuss saying, like, I don't know quite how this works. So like, have something there. If it's about the application, make sure you have some sort of draft of your application. Sit down, think about things. Like, quite a few of you have read up on many different supernova topics, and so I think that's great. And so for now, like, write the application. That's, I think, the most important thing that we think. Okay, great. I'll see you guys later. Bye from, I guess, the group. They wave in the background. Bye. Okay, I'll see you maybe next week, and let us know and get how things go. Bye.